So the handouts are just if you missed the last class, they're nothing new. Okay, so this is the handouts from last time. On the reverse side, we worked on the basic exponent rules that we are now reversing with radicals. Okay. And on the back, spot the mistake, I suggested that especially to practice your exponent rules, that you consider the sort of homework over the weekend and worked on this. I'm going to do a couple of them together, just make sure we're on the right track. And then this bottom right box is comparing, adding, and multiplying, which is going to transition us with what we're doing today. Okay, so let's look at this first one in the top left. And this person, this is the wrong answer. Okay. Where is the mistake? First one thing is what operation is being used here. That's always the first thing your mind should register. Is it adding, subtracting, multiplying, dividing, powering? What is the operation that's being done here?
Multiplying.
Right. So this is going to involve a product rule. Okay? If it's multiplying, we need a product rule. Okay? And so what mistake was made here that makes x to the 7th not the correct answer? Right. Yeah. And it's actually a very real one. It's not even imaginary, but we just don't have to write it. But put it in because you have to do the math with it. Okay? So the mistake was right there. So make some mark of what the mistake is. The mistake is forgot the exponent of 1 on the middle term. So being that this is a product, what should they have done?
Add the exponents.
Right, add the exponents, right? So they just added 3 and 4. So instead, add the exponents 3 plus 1 plus 4. So the correct answer should be x to the 8th power. So that's the idea with, that's one of the common mistakes with exponent rules when you're talking about the product or the quotient rule is making sure that when you're adding or subtracting those exponents that you write in any ones that you don't have to write, but they are there and you have to do the math with them.
I wrote it down differently.
Okay.
I just put take away an x.
Take away an x.
Yeah, that extra x that's there.
Uh-huh.
Instead of adding the exponents and just getting x to the 8th, I just kept the x to the 7th and I took away the x.
Okay.
Would that have counted too? Or
That would have made, if you wanted this to be the answer, taking that away would have made it correct. Yeah, that's another way of thinking about it, yeah. Because you recognize that this is worth 1x.
Yeah.
Do you also understand how if you leave it there, it adds up to 8?
Yeah.
Yeah, so yeah, there can be more than one approach to it. I hadn't had anyone bring that up before, but that's absolutely another way to approach it. That would make it correct. Yeah. This would be correct if this were not here. And as long as you understand why, that's the big idea. Yeah. Good thinking. Alternative ways of approaching it. That's the nice thing about math is it has very strict rules, not ambiguous rules. The rules are always the same, but there's often some multiple approaches. The more comfortable you get, you find different ways to approach or look at a problem, but always using those same unambiguous rules. Right, let's look at this one. The other one, let's look at the one right underneath it. What is the operation in this one? Addition. Now that changes everything. Okay? When you have product rule, you're multiplying terms. What do you have to have in order to make this 3 plus 1 plus 4 is 8? Like bases, right. If you don't have the same bases, if this was x, y, and z, you'd be out of luck. Okay? You could take away the dots and write them next to each other, but you could not smoosh together, could not combine the exponents. You must have like bases. Now, what the operation here is addition. When you add, that's a little stricter. What do you have to have besides like bases? The same exponents, right. Because you're not messing with the exponents. Okay? So what is the mistake made here?
the addition should multiply.
Yeah, so they treated it like it was a multiplication problem, right? And so, okay, so that's a good way to put it too. So in this case, they treated it like it was using the product rule, or multiplication. Okay. But it's not the product rule, what should they have done instead?
Just kind of make it the same. Factor it.
Combine them.
Combined, like combine the coefficients?
X, 3, 4,
Mm-hmm.
X, 4.
Okay. So, well, they kind of did that. They added those exponents to be 7.
Multiply.
Multiply what?
That 3 and 4.
Okay. Well, that's definitely what we do for the power rule. X cubed to the 4th power be x to the 3 times 4. But this is not a power rule. This is adding. Now, as we pointed out, what we needed for multiplying for the product rule is just like bases.
Can you not do nothing?
Exactly. Right. Yeah. Because here, for product rule, you just need like bases, then you add the exponents. But when adding and subtracting, you require more than just like bases. You also, as pointed out, you require the same exponents. Do you have the same base? Yeah. Do you have the same exponent? No. Therefore, can you add? No. Because you require, just like bases for multiplying, you require like terms for adding. Now, this is something, actually, this is one of those things, a lot of what we're doing today is something your brain already knows, but when you put in some other things, it forgets it knows it. Okay, you already know about like terms. For example, if you had 5x plus 2x, are those like terms? Yeah, they're both x's, right? What does that equal?
7.
Yeah. Did anybody think 7x squared? No, right? I mean, this is something that becomes more automatic now. 5x and 2x means we have 7x. Okay? 5 apples and 2 apples is 7 apples. Apples is still apples. X is still x. The variable didn't change. Now, what does your brain do when you see this? 5x plus 2y. Yeah, you're done. There's nothing you can do. You leave it alone. Unlike terms, unlike terms. Okay? Your brain automatically now sees, oh, x's are the same. I can add the coefficients. X and y, those are different. I can't combine them. Same rule, but it's kind of messing with our brain. Now we're not dealing just with x's and y's, but we're also dealing with exponents. Okay? A like term not requires only the same letter, but it also requires the same exponent. Okay? So if these are unlike terms, like this, x and y are unlike terms, but x cubed and x to the 4th are unlike terms. Okay? So all you can do is just, what should you do instead? Nothing. Yeah. It's already simplified. Okay. Already simplified. It's as simple as it gets. And now, don't put no solution or undefined or anything like that. Those terms don't apply to this. And that's a common mix-up. It's like, oh, if I can't do anything, it has to be some sort of official term, null. Yeah, not really. No, it's perfectly real. It's perfectly fine. It just can't be simplified to that. This is perfectly real. It's perfectly defined. It's a thing. It's just already in lowest terms. It's already simplified. So it's treated like the product rule, but the mistake was because of the addition, you need like terms. Okay? So what should you do instead? Well, you don't have like terms, so you walk away. You do nothing. And the correct answer then is, like I said, that's correct. It's not null or no solution or undefined, blah, blah. No, it's just, that's it. There's nothing to do. Now, leave the other ones open. Given time, we can come back and revisit those. And I'll also be posting the solutions even if we don't get to them in class. But that's the idea. Find the mistake. Circle the mistake. How would you correct it? Okay? Why is it the mistake? Because you want to really train your brain, whether we're dealing with x's and y's or a combination of exponents and x's and y's. We really want to be very conscious of when we're multiplying versus when we're adding. Because the rules, like in so many different areas of math, are different whether you're adding or whether you're multiplying. So sliding down here to the bottom right, it's exactly what we want to focus on, because we're going to make that transition today with radicals. What operation do we have on the left-hand side here? All right. And on the right-hand side. Yeah. So our rules are going to be different. So as we already noted, what do you need to have when you add? Same base and same exponent, I heard. So you must have like terms. Okay? Now, like terms are very strict. That is, same base and same exponents. That's what a like term is. The whole thing looks the same. Now, when you have those like terms, what do you do? For example, if we had 5x and 2x, what do you do? Add the, not the bases, coefficients. Right, yeah. You can practice that vocabulary, right? Coefficients. So if you've got like terms, then you add or subtract. So we'll just say combine. Okay, so combine might be add or subtract, depending on what you're told. Combine the coefficients. What do you do to the variable? Yeah, you just write down what it is. Yeah, 5x and 2x is 7x. 5 apples and 2 apples is 7 apples. Okay, it's not apples squared. Okay, so you combine the coefficients and you keep the same variable. Okay, the same variable, same exponents. Okay. So the term itself doesn't change. Now for multiplication, what do you need?
Just same base.
Right. This isn't as strict, you just need the like bases. And if you have like bases, what will you do to the coefficients? So that you're multiplying, what do you do to the coefficients?
Add the coefficient.
Well, this is a multiplication problem, right? So the coefficients, here you'd have 2 and 5 would be,
You multiply this thing.
and this would be 10. Okay? So you either add the coefficients or you multiply the coefficients. Yeah, the coefficients specifically. Yeah, the vocabulary. Right. Yeah. So you multiply the coefficients, just regular multiplication. And then for the exponents, yeah. So you have a variable with a new exponent on it. All right. So with that in mind, do these 8. Notice how it's the same terms, but one's addition and one on the left is addition, right is multiplication. Start training your brain to think addition or multiplication, addition or multiplication. It changes everything. Either way, we treat numbers like numbers. The coefficients are either added or they are multiplied. If you have completely like terms, then you keep that same term. This, 2 plus 5 is 7, and it's still x cubed. Here, 2 times 5 is 10, but we also, because it's multiplication, have to add the exponents, and we have a new exponent, like base of x, but with a new exponent of 6. Now, nothing we could do in these last two when we're adding, because these are unlike terms, either x squared and x to the 5th at different exponents or different bases. Either way, they're not like terms. We walk away. Here, with product, we can multiply the coefficients, add the exponents. Here, these are unlike bases. It's still all multiplication. We just put them next to each other. We just don't change any exponents. Questions? Confusion?
Do we have it? Are we gonna ever have questions like where we get the 10x, basically like the answer, and then we have to, what do you call it, like?
Oh, like reverse it?
Yeah.
Yeah, and that's
To get the 2x.
right. I'm not going to give you something like this and say reverse it to this. There's several ways you could do that. This could be a 2 and a 5 or a 1 and a 10. And this could be x and 1 and 5, 2 and 4, 3 and 3.
The word is reverse.
Right, the reverse, right. Now, for something like this, no, I'm not going to have you reverse it to something like that, but the idea of reversing both the product and the power rule is exactly what we're doing with the radicals, so we can root something. Because rooting is the inverse of exponents. So if we reverse power, reverse product, just like on the other side here, these reverse examples were specifically to show how you can break one thing down into, basically this is factoring x to the 12th. Just like 15 is 1 times 15 or 3 times 5, x to the 12th is x to the something times x to the something, lots of combinations. This is one of them. And power rule is just like we multiply the powers to get that, we also, if we start with that power and we want to divide it, we want this outside power to be that, we divide. The opposite of multiplication is division to find out what the missing thing is. Yeah. So that's going to help us because powers, exponents, and roots are inverse operations, just like multiplication and division are inverse operations, or adding and subtracting inverse operations. We can reverse the process to root something. Yeah. But just sort of randomly like that, no. I mean, I want you to recognize, yeah, you could do that, but that's not relevant to why we're using this. Yeah. Okay. And this is fundamental right here. These two right here. 1x plus 1x, 2x. 1 apple and 1 apple is 2 apples. Okay. X times x is, so this was like a 1x and a 1x. Add the coefficients because the bases are alike. Here, like basis, like same basis, same exponent, so just to combine the coefficients. Here, 1 times 1 is still a coefficient of 1. That doesn't change anything. But these are x to the 1 plus x to the 1 plus 1. Okay. So 2x versus x squared, two totally different things. The most basic sort of example of the difference between adding or multiplying. Okay. Okay with that? So, let's do some warm-up problems, some problems like we had last time that will transition us then into the quotient rule and then into adding and subtracting. Okay. So where we left off last time is, let's say, and here's kind of an example that we didn't have in class, but you saw in homework. It's not that different. It's just got another element to it that we didn't directly discuss. So x to the 36, y squared. So on the outside, this is not a cube root. See, it's written bigger. Okay, that's a coefficient. Okay, so this is like 3x, except instead of x, we have this whole radical. 3 times a radical. So we're going to treat that. Often you'll hear me refer to that as a coefficient, like with in air quotes. Okay, because it's not technically a coefficient, but we treat it like one. There is actually a multiplication sign right there. We just don't have to write it, but we could. So if there's already a coefficient here, but then we root and release something, whatever we root and release will multiply times what's already there. And with all the examples we worked with last time, the only thing on the outside was a 1, which we didn't have to write. Okay? But if there's something else there, it's all multiplication, and that will become a new coefficient. Okay? All right, but that aside for a second, what we started off with in 11.1 is the idea of what is a perfect square, perfect cube, etc. Okay? So the way to attack these problems, if you're told to simplify, is note how many elements do I have underneath this radical sign? 3. Yeah, we got a number, and we got an x, and we got a y. So ask yourself first, is this a perfect square? Yes. The number is. What about this? Yes. And this?
Yes.
Yeah. We have an index of 2. Huh? So we're asking, the way to reverse a square root is with squares. Okay? These are inverse operations. Exponents and roots are inverse operations. Okay? So we go in both directions and reverse one with the other. So if this is a perfect square and that's a perfect square and that's a perfect square, are we going to have any leftover bits? Are we going to be able to root and release everything? If everything's a perfect square, is the radical going to go away? Yeah, if it's a perfect square, then you can square root it, and no more radical sign. Okay? So first thing I want you to notice is, oh, that's the index. So ask, is it a perfect square, perfect square, perfect square? If everything's a perfect square, you know there's not going to be any leftover bits. So your only job right now is to unsquare everything. Okay? So the next step, and we'll leave this on the outside, square root, and even though you don't have to write it, we'll go ahead and put in the 2 because the whole point is we're going to be canceling out the 2's. We cancel out the index with the exponent. Once we have an index that matches an exponent, boom, it obliterates the radical. Okay? That's what I refer to as root and release. So I've got 3 elements under there, so I'm going to make 3 houses. Here's the house for the number, and I'm going to turn it into a square. Here's the house for the x, leave a little room, turn it into a square, and here's the house for the y, leave a little room, turn it into a square. The whole point is if there's a square here, and these are all turned into squares, then all those squares in the index of 2 are going to cancel out and release the rooted numbers. So we're basically square rooting each of these things. We're reversing the process. What's the square root of 10? I'm sorry, what's the square root of 100? 10. Now be careful here because a lot of instinct is often to divide this by 2 because that's what you're doing with the exponents, not with the number. This is not 50. Okay? It's your square numbers you square root. Okay? So I'm rooting this 10 and then check 10 squared. Yes, that's 100. Check. If you put 50 here, 50 squared is 2,500. Not check. Okay? Now with exponents, though, if you've got variables with exponents, you want to see, can I divide this into 2 groups? Okay? That's kind of like thinking reverse product rule. Okay? X to the something times x to the something would be the something plus something. So basically, if you can divide it into 2 groups, okay? And the shorthand for the product rule is the power rule. Okay? So if it is an even exponent, if it's divisible by your index, then it is a perfect square. Okay? So, and I know it's a perfect square because if the product rule says multiply these 2 things, the opposite of multiplying is dividing. So what would go here to make this still true? Right. And do a quick check. 18 times 2 is 36. Check. What would go here to make this still the same? Yeah. I didn't change the value of anything, just unsquared everything. Okay. Now once you do that, everything's in its little houses, then the index and the exponents cancel out. It obliterates the radical, and what's in the parentheses is your answer. So you've got 3, don't forget that on the outside, times 10 x to the 18th, y to the 1, or just y. Now because we did have an outside coefficient here, we're not quite done, what's the coefficient of our answer?
38.
Yeah, exactly. It's all multiplication. We just have to combine the outside one. Now we don't do 3 times 100. Anything, and this is going to come up again and again, anything outside a radical and inside a radical cannot mix. Okay? This is not 100, it's 10. If you do 3 times 100, that's an illegal move. Once you root and release it, now it's free and you can combine them with multiplication. X to the 18th, y. Okay? Okay, that was a square root. Now this is not a coefficient of 3. See, it's small and raised. Our index is 3. So before you go any further, because if the answer to this is no, then you're going to have an extra step. But check, you've got 1, 2, 3 elements. Check and see if they're all perfect cubes. Perfect cube? That's not a problem, it's negative, right? No. It's okay, you can have triplet negatives, odd negatives, still give you a negative, not a problem. If this were an even number, this would be non-real, and you just walk away entirely. Don't do anything. No matter what else is going on in here, if this is a square root or any other even index, a negative on the inside means it's non-real. Nothing else you can do. And then, is this a perfect cube?
Yes.
Yeah, because you can divide it into 3 groups, triplets. Okay? So if your exponent is divisible by your index, you know it's a perfect, whatever that root is, in this case cube. This one? Yeah. So everything, your 3 elements are all perfect cubes, so you don't have to separate leftover bits. Okay? Just uncube everything, root, and release. All right, give each element its own house with a cube on the outside, and then make it true. Once you make it true, what's in the parentheses is your answer. Right, because if you've got a negative radicand, then for an odd x index, a negative radicand gives you a negative base. Okay. Because 2 times 2 times 2,
How'd you get
4. Right. It is negative, however, it is not 2, it is 4. Yes. Yeah, 4 times 4 times 4 is positive 64, negative 4 times negative 4 times negative 4 is negative 64. Now, don't then let your brain automatically try and unsquare that or do anything else. A lot of times, especially with square roots and double squares, 81, you unsquare to 9, and then you automatically want to make it 3. That's double squaring, double dipping. Okay? Careful with that. You unroot it one time, that's it. Okay? And there's your answer, because the 3's obliterated. Negative 4, x cubed, y to the 4th. X to the 7th, y to the 8th, and negative 5, cube root, negative 24, x to the 8th, y to the 10th. I just put in a dot for clarity. It's automatically multiplication even without that, but when handwriting, especially if you've got something besides a square root, for clarity, just to be really clear. Okay. So you don't mix up exponents with indices. Okay. Now, same as before, you're asked to simplify this. You see what the index is. And you ask yourself, are all of these elements, I've got 3 elements, are they all perfect squares? No. If at least one of them isn't a perfect square or more, you're going to have leftover bits. So instead of going right to unsquaring everything, you need a second step. You first have to separate. You have to sort. Perfect squares on the left, leftover bits on the right. Okay. Draw a bar, keep our index written in, put a dot in the middle, okay, and we're going to sort. So you got to look at 90. Now, whether you make a manual list or on your calculator, either way, go off to the side and do it. Don't make this area too chaotic. Okay? So I'd go off to the side, get out of the way, make my list, calculator or manual. If you do it manually, it's just like the calculator, but you got to go in order like the calculator so you don't miss one. Always start with 1 times itself. It's even. 3 is a factor. 5, yeah, because it ends in 0. 6. And I'm looking down this, I'm looking for the biggest. Once I hit a perfect square, I know I'm done. Okay, but I haven't yet. 7, 8, 9, 10. Well, I already got it. That's how I know I'm done. If you go in order, you know when you're done. This is the same list that'll show up on the calculator. You just have to ignore the decimals in the calculator. Okay. Remember, you're only looking for positive ones. Do I see a perfect square?
Yes.
9, right. So there wasn't one on the right-hand side, so I start coming back up the left hand. Oh, there is one. If the answer were no, then 90 would just not be it. You just put all of it on the right. But no, 90 can be broken up into 9 times 10. What do I write on the left? 9. Not because it's bigger or smaller first here, but because it's the perfect square. And the leftover bit goes there. 9 times 10 is still 9.